In this lecture, we will look at another type of one-stage op-amp called the telescopic op-amp. Now, let us first start with the original one-stage op-amp and see how we can improve upon it even further. So, this is the one-stage op-amp, regular one-stage op-amp that we have been studying so far. Now, of course, the DC gain of this op-amp, which is a low frequency gain, is GM1 into RDS2 parallel RDS4, and the output node is the node which has the dominant capacitance, which is normally the load capacitance CL. Now let us assume that I want to increase the gain of this op-amp. So I want even larger DC gain. That is our goal. So now, as you can see, this is of the order of the DC gain as we have it now is of the order of the intrinsic gain of a device. So clearly, you will have to make a circuit change to get even more gain because you have now reached the limits of the gain that every device can offer. And from a single stage, it's not easy, or it's not from a single device, it's not easy to get any more gain. Now, of course, there are circuit techniques that we know. Now, before we go there, we will now understand or quickly review the progression of the signal through the circuit. So, let us say that the inputs are Vt by 2 and minus Vt by 2. We first need to understand the progression or review the progression of the currents through the circuit so that we can see how to improve the circuit. So, as we pointed out, the common source node is a virtual ground, and each transistor now has a current GMVT by 2 in the directions shown. And in parallel with CL, I will also explicitly show the output resistance, which is RDS2 parallel RDS4, so that we understand where the current is flowing. Now, the current through M1 creates a small signal voltage at node X, and this also causes a current to flow through M4. So, you need to understand that this portion of the circuit comprises a current mirror, and it is an active load. You don't have any resistors, you have a PMOS load, and it comprises a current mirror. Now, the current through M3 is the same as the current through M1, which is GMVB by 2, and that current gets mirrored into M4. So, the current through M4 is also GM1 VT by 2, and therefore the total output current IO is GM1 times VB. So, as you can see, the function of the active load, the function of the current mirror, is to take the current from the left hand side and pump it back into the right hand side in a constructive manner, so that you get even more signal current flowing into the load. The second thing to note is that the output voltage is generated by passing this current through the load. Now, let us assume we are looking at the output at low frequencies. at low frequencies, the capacitance presents an open circuit and the output resistance, the output voltage is nothing but I0 times RDS2 parallel RDS4. So this tells us that the output current flows through the parallel impedance of M2 and M4 to create the output voltage. So this is GM1 into RDS2 parallel RDS4 times VD. Now this shows us where the gain is coming from. The signal currents need to be additive at the output node. So that is important. From both halves of the circuit need to add at the output node. So that is an important requirement. And number 2, the output resistance needs to be high. Needs to be high to achieve large gain. Large DC gain. So what this means is that if you want to increase the DC gain of the op-amp, you only have two options. You have to either increase GM or you have to increase RDS. Now we are now very close to the intrinsic gain of the device. So we need to find out ways to improve the RDS of the device. The GM of the device, it is much harder to increase. We will now try to increase the output resistance of the op-amp. So the first structure that we look at is one that we have seen before. So if you take a common source transistor, which is M1, and include a common gate transistor M2 in series with it, it turns out it behaves in such a manner as to increase the output resistance. This is of course the small signal output resistance. So again, let us quickly review this. So let us say at the gate of M1, I have VB1 plus Vin, and at the gate of M2, I only have VB2. I want to analyze this structure to find out the output resistance of this structure. So let us draw the small signal equivalent circuit. This particular structure is called the Cascode structure. So this will be a quick review for us because we are going to use this to increase the output resistance of our op-amp. So we want to find out the output resistance of our particular structure. So just wanted to point out that Vin will be set to 0. So this current source is equal to 0. This is RDS1, this is RDS2, and this is GM2 times VGS2. Now let us denote this node voltage by Vx. Therefore, IB2 is GM2 times VGS2. This is clearly nothing but minus GM2 times Vx. Now we want to find out the overall output resistance of the structure. Now let us say we excite it with a test current source, I test. So the total current flowing into the circuit is I test, and therefore the value of Vx, of course, is also equal to I test times rds1. This is because the current I test flows into this node, into the output node. It splits between these two devices, these two components, and combines back up to flow through rds1. So the current through rds1 is also I test. Therefore, Vx is equal to I test times rds1. Now, therefore, the value of the drain current through M2 is minus GM2 into rds1 into I test. Therefore, the output test voltage that is generated, denoted by V test, can be determined. The voltage V test can be determined by applying KCL at the output node in the following way. So the sum of all currents at the output node has to be equal to 0. So I test is the current flowing into the output node. So I test splits as minus GM2Vx plus V test minus Vx by rds2. So the two currents you have minus GM2Vx and V test minus Vx by rds2 flowing through the resistance rds2. So this means that I test times rds2 is minus GM2 rds2 Vx plus test minus Vx. And now we can also write I test in terms of Vx, as since Vx is equal to I test times rds1, we will substitute this back into these 2 points. So I test times rds2 was V test minus Vx into 1 plus GM2 rds2. This is V test minus I test into rds1 into 1 plus GM2 rds2. Therefore, I test into rds2 plus rds1 into 1 plus GM2 rds2 is equal to V test. Therefore, V test by I test is our out. This is nothing but rds2 plus rds1 into 1 plus GM2 rds2. Now we can make some approximations we can say that 1 plus, so we can say that GM2 RDS2 is much larger than 1, and we can also say that RDS1 and RDS2 are of the same order of magnitude. In such a case, we can say that the output resistance is approximately equal to GM2 RDS2 times RDS1. So in other words, we have neglected this term first, and we have also said that this term is much larger than this term. Now this is a circuit that we want where the output resistance has been increased using a circuit technique alone. So now let us go back and try to implement this in our op-amp. So if I were to build an op-amp, now I know that my input should now have a cascode portion, because the impedance looking down needs to be as large as possible. So now I am going to connect both these voltages to the same voltage. I'll call that VB2. So this is the bottom portion of the circuit. So I have now managed to increase the impedance looking down. Now I will now have something up here. The block up here needs to perform two components. So first of all, it needs to build a current mirror action. So this is something I need from this particular block. It also needs to have high output impedance. This block also needs to have high output resistance. And for example, if I were to take this circuit, let us take an example. If I were to take this circuit and connect up a normal current mirror. Let us try that first. So I'll draw that in blue. So let us say I were to do this. If I were to do this, so let me call this M5 and M6, I will clearly get the current mirror action that I have been looking for, but I have a problem. The resistance looking up is RDS6, whereas the resistance looking down is GM4 RDS4 times RDS2. So RDN is much larger than R up. This means that if I look at the gain of this op-amp, this gain would be approximately GM1 times R up. So I have not moved that much. I would get, earlier it was half the intrinsic gain of the transistor. Now I would get approximately the intrinsic gain. This is a difference of only around 6 dB. So this, I want to increase the gain even further compared to this. Now please note that what is left unsaid is that this particular cascode structure has the same GM. So if I were to look at, I have so far looked only at the output resistance. The output current flowing into the circuit is GM1, so it is the GM of the lower transistor times Vin. So please note this. So therefore, since the DC gain has not increased that much, we need to come up with an even better circuit that will improve the DC gain even further. So now let us look at the other circuit that we have seen before, which is a cascode current mirror. So I start with a simple current mirror. This has an output resistance of RDS. And now I need to add a cascode device to improve the output resistance of the current mirror even further. So I move to a cascode current mirror, which looks like this. So this is the cascode current mirror. So this has a very large output resistance of approximately GM RD squared, if I assume all of them are identical. And finally, from the cascode current mirror, I move to the high swing cascode circuit. The difference is that the feedback is taken from this particular node and in this particular case the gate of the upper transistors is tied to a bias voltage such that this is approximately 1 VDSAT, this is approximately 1 VDSAT. Therefore, this particular circuit has high R out and high swing. This is called the high swing current mirror or the low voltage cascode current mirror. So this is the circuit we are going to use, except we are going to use the PMOS version of this circuit. So let us now build the Cascode OpAmp by filling in the PMOS current mirror. This is VDD. Call this VB3, and now we have an op-amp that could potentially have large DC gain and proportionally high swing, because we have used a high swing cascode. Now we are going to analyze this op-amp with a small signal differential signal applied to the gates of M1 and M2, and we will really see if it has large DC gain we will really see if it has